Okay, in this video, we will be talking about angles and their measure. First thing we're going to do is look at degrees and minutes and seconds. Just another way to measure an angle in more specific terms. So if you have something like 61 degrees, 42, what looks like an apostrophe, is minutes, and 2 with what looks like quotation marks are seconds. So what looks like an apostrophe is minutes, and then what looks like quotation marks are seconds. And I want to approximate what this is. That's a quotation mark, not so good. So to convert 61 degrees, 42 minutes and 2 seconds into a full degree measure, this is going to be 61 plus, there are 42 minutes in an hour, so I'm going to add 42 over 60, plus there are 60 seconds in a minute, and there are 60 minutes in an hour. So 60 times 60, which is 3,600. So 60 minutes in an hour, 3,600 seconds in an hour. So when you add this all together, you get approximately 61.7 degrees. So this is the approximation, but 42 minutes and 2 seconds is the exact value. They use the degrees and minutes a lot in navigation. They also use it in like latitude and longitude, so it does exist. That is degrees, minutes, and seconds. Okay, now we're going to look at radians. So you can see I have a nice circle. There's no way I'm going to freehand that. It would be atrocious. So let's look at radians. Radians are another unit of measure. So sometimes we have miles, sometimes we have kilometers. Sometimes we use radians, sometimes we use degrees. So the first most important thing is, what is a radian? So I have a circle here with some radius r. I don't know what the radius is, and I don't really care, frankly. Okay, so I'm going to use a piece of string here, which you may or may not be able to see, but I have a piece of string, so hopefully you can see my little string. And this string is the length, is the equivalent of the radius. So a radian is formed when you have this radius, and you have the radius from edge of the circle, where my finger is here, and it reaches, and you kind of like spread it around the edge of the circle, which eventually becomes the circumference. And the edge of the string ends about here-ish. So you can see my string did not change length. From the center to the edge is the length of the radius, and then I just spread it out along the edge of the circle. And so these are the same. One's linear and one's curve. When you connect those back together, this is the measure of a radian. This is the measure of a radian. So how do you figure it out? Well, how do you figure out, the difference between, or the measurements between radians and degrees? So circumference of a circle is 2 pi r. So, r is involved in circumference, but the r on the edge of the circle is the same as the radius. Well, that is equal to 360 degrees, because there are 360 degrees in the circle. Divide both sides by 2 pi, and the radius, which is the measure of 1 radian, divide by 2 pi and reduce, and you get 180 over pi. So the measure of a radian is equal to 180 degrees over pi. So let's just practice doing a conversion. Let's just practice doing a conversion. We'll stick with 30, 60s, and 45s. Those are the ones that you're going to be using the most. So let's say I want you to convert 120 degrees to radians. It's in degrees. I want to put it into radians. So take 120 degrees and I'm going to multiply it by pi over 180. Why pi over 180? Because I should say pi over 180 degrees, because then the degrees will reduce. This is, you can skip this step, 120 pi over 180, which is 2 pi over 3. This is all going to lead us, if you haven't figured it out yet, into the unit circle. Unit circle is all of trig, right? So the class is trig math analysis. Well, we just done all the math analysis. Now we're getting into the trig. Let's go the other way around. So in radians, let's say I have, how about 5 pi over 4, and I want to convert that to degrees. In general, not always, in general, pi is part of the angle measure, it's in radians. It's always in degrees, obviously, if you have a degree symbol. Don't forget the degree symbol. If you forget the degree symbol, you are automatically implied that you are in radians, and you will lose points on, quiz and then final exam. Degrees are required if you're in degrees. So I'm going to multiply 5 pi over 4 times 180 degrees over pi. That way the pi's will reduce. 25, I think that's 225 degrees. If it's not, you'll tell me. Okay. One thing that we're going to talk about quite a bit in this section is arc length and area of a sector. Arc length and area of a sector. Okay, so arc length is the length of any arc alongside the circle. The arc might be, it doesn't have to be equal to r, but the arc length is some piece of the edge of the circle. Arc length is r theta. Here's the kicker. Must be in radians. You learn this in geometry a long way because they don't teach you about radians, I don't think, in geometry, but radians times radius. So arc length is think of it as the edge of the circle. Part of the circumference. So arc length would be, you have a giant cookie and you want to put frosting on the edge of the cookie. That's arc length. You have a hot tub and you want to put bumpers along the edge of the hot tub so that you don't hit your head. That's arc length. Then we have the sector of a circle. The sector is an actual piece. A sector is the actual piece, the area of a piece. An area of a piece of the circle. And that is a sector. I'll move my hand in a second. Sector is the area of the piece of a circle. And that is found 1/2, oops, no, that's supposed to say a half, sorry. 1/2 r squared theta. 1/2 r squared theta is the sector. There is a proof of how to get 1/2 r squared theta. If you're interested, that's on page 359. And arc length you've done in geometry, but if you'd like me to, I can show you where that comes from after the video. Okay, so radians, degrees, minutes, seconds, arc length, and then sector. Okay, let's move on. So the two more important concepts in this section are linear speed and angular speed. Okay, we'll start with linear speed, and I'll do angular in a minute. Okay, so linear speed, it's a rate. Linear speed is a rate. How fast are you going? Point A to point B. How fast are you going? Point A to point B. Well, you already know this. You know distance equals rate times time. You know distance equals rate times time. All right, well, if I want to find the rate, don't I divide both sides by t? If I want to know the rate, rate is distance over time. That's exactly what linear speed is. However, we have to make it interesting, and we need to use different variables because r is now radius, so it's hard to keep track what everything is. So instead, we use v is equal to s over t. V is equal to s over t. V is the speed. S is the distance. And T is time. Now, T could be in any measurement. It could be in hours, it could be in minutes, it could be seconds. There's no set, like when we're doing interest where T is time in years, not for this. Let's look at angular speed. Okay, angular speed is the speed at which something is rotating. The speed at which something is rotating. So linear speed is from point A to point B. Angular speed is the speed of rotation. It's the speed of rotation. You know, it just occurred to me that you guys may learn about this if you're in physics. Maybe you do. Okay, funky, weird looking letters. Like this W, but the top part is like squeezed in. That's a terrible terrible description. This is Greek lowercase omega, and that's equal to theta over t. Well, theta is an angle. So what's the speed at which the angle is changing? So theta is the angle in radians, always in radians. And of course, t is time. If you've ever been on any kind of amusement park ride, like for example, the teacups in Disneyland. The teacups in Disneyland, like they turn you around in circles, in circle, in circle, in circle. That is angular speed. The speed at which you are spinning, that's angular speed. I'm going to pause the video to give you an opportunity to get your book so I can go through some word problems. Let's start with page 362, number 92. You do not have to draw a picture. I think it's super helpful if you do. And I am very artistically challenged. So I'm going to be honest that your best bet is to look at some of the pictures in the book. I'm very, very bad at the visual part of it, so I apologize. Page 362, number 92 says, a pendulum swings through an angle of 20 degrees each second. If the pendulum is 40 inches long, don't even know what they're asking me yet, but I'm going to write it down. The length of the pendulum is 40 inches. How far does its tip move each second? Round to 2 decimal places. Okay, so I have a pendulum and it's 40 inches long and it is moving through an angle of 20 degrees. The question is, how far does it move? It's not asking for any speed. Just want to know how far it moves. This is arc length. How far does it move is arc length. This is not asking me for any type of speed. Okay. So I have 20 degrees per second. Arc length. R theta. Theta needs to be in radians. So I'm going to change 20 degrees to radians, which is pi over 180. This ends up being, oh, sorry, times the radius. I forgot about that. Times the radius. So I need to multiply by 40. Times, sorry, let's just try this again. 20 degrees per second times pi over 180. That's going to give me the measure of the angle in radians. Notice that the degrees are going to reduce out. Times 40 inches. Reduce, you end up getting 40 pi over 9, which is to the nearest hundredth 13.96 inches per second. I converted 20 degrees to radians by multiplying by pi over 180. The 40 inches is the radius. Multiply the whole thing across. You get 40 pi over 9, which in reality doesn't make a whole lot of sense. So you should multiply through by pi and get 13.96 inches. Okay, let's look at number 100, which is going to ask us for some speeds. I'm going to move this up. Okay, number 100. So number 100 says motion of a circle. An object is traveling around a circle with a radius of 2 meters. If in 20 seconds, the object travels 5 meters, what's its angular speed and what is its linear speed? Okay, so here comes my very challenged picture. I can't laugh at myself. Who can I laugh at? So the radius is 2 meters. And in a matter of 20 seconds, it travels 5 meters. So let's do this. Travels 5 meters, and that takes 20 seconds. Okay, so they want to know angular speed and linear speed. Okay. Angular speed, how fast is it rotating? So this is going to be, nope, that's linear. Oh no, that's right, sorry. The speed is going to be equal to theta over time. Okay, so first I need to find theta. I know that time is 20 seconds. I know that time is 20 seconds. But to find out the measure of angle theta, we need to go back to arc length. So I'm going to put that off to the side here. So the arc length is equal to radians times the radius. The length of the radius times the measure of the angle in radians. Well, I know that the arc length in this case is 5 meters. The arc length that they gave me was 5 meters in 20 seconds, which we'll take into account in a minute. And then the radius, which I'm given is 2, is equal to theta. If I can't figure out the measure of angle theta without using the formula for arc length. So this will tell me that theta is divided by the arc length is 5. That's equal to the radius, which is 2 times theta. So theta is equal to 5/2. So let's plug that in now to find our angular speed. So my angular speed is going to be theta, which we just figured out is 5/2 over the time, which is 20 seconds. Divide this out and you get 0.125 radians per second. Let's take a look at the linear speed. Linear speed, in my opinion, is not nearly as complicated as angular speed. Can you see that? Yeah. So linear speed, distance equals rate times time with just some funkier letters. V is equal to S over T. Five meters over 20 seconds, which is 0.25 meters per second. Let's do one more. Let's look at number 102. The amusement park. A centrifugal, I hope I'm saying that right, a centrifugal force ride similar to the graviton spins at 22 revolutions per minute. Oh, no, thank you. The diameter of the ride is 13 meters. What is the linear speed of the passengers in kilometers per hour? Okay, so linear speed. V equals the distance divided by the unit of time. Okay, watch me draw another bad circle. These aren't so bad. On the whiteboard, they're pretty atrocious. 13 inches, I think. 13 inches? Nope, 13 meters. Of course it's meters. Can't be on a, I wouldn't want to be in an amusement park ride with 13 inches. That wouldn't work. 22 revolutions per minute. .22 revolutions per minute. The diameter is 13 meters. What's the linear speed? Okay, so I have to figure out S. S is the distance. Okay, well, around and around and around 22 times. So that's going to be circumference, which pi d. So 1 revolution is 13 pi meters. That's 1 revolution. Okay, but this says that it's 22 revolutions per minute. So I'm going to take my 13 pi times 22 meters. Sorry, yeah, per minute. Okay, so really, you multiply that out, you get 286 pi meters per minute. One revolution, that's circumference. Diameter is 13, that's pi d. So 13 pi meters times 22 because you're doing 22 of those revolutions every minute. The directions say, what's the linear speed in kilometers per hour? In kilometers per hour. So if this is 286 pi, which is about 898.5 meters per minute, and they want to know per hour, times 60 minutes per hour. You guys do this in chemistry, not significant figures. I forget what it's called, but you do this in chem. I hear all the complaints about it. Times 60 is 50. Oh, no, and you know what? Let's take care of the meters at the same time. 1 kilometer is 1,000 meters. Let's just take care of the whole thing at once. Multiply that whole thing out and you get 53.9 kilometers per hour, which I think ends up being like 30 something miles per hour. If I've done the conversion right, it's like 30 something miles per hour, which is pretty fast, I think, which is why I don't go on roller coasters. Those teacups, just talking about them makes me nauseous. There you have it.